Welcome to Visual Algebra Lecture 5.11, the first two Sylow theorems. The three Sylow theorems tell us about the structure of a group's subgroups of prime power order, which are called p-subgroups. The first Sylow theorem tells us that p-subgroups of all possible orders exist, and they are nested. Each non-maximal one is contained in a bigger one. In other words, they come in towers in the subgroup lattice. The second Sylow theorem says that the maximal p-subgroups, that is the tops of these towers, form a conjugacy class. This means that there is a unique p-group tower for each prime dividing the order of G. The third Sylow theorem imposes strong restrictions on the size of this conjugacy class, but we'll save that and the applications to simple groups for the next lecture. Let's get started. Let's start by recalling an open-ended question that we asked earlier in this course. It was at the end of chapter 2. I asked what group structural properties are possible and what are impossible, and how does this depend on the order of G? One approach to this is to decompose large groups into so-called building block subgroups. For example, given a group of order 72, which is 8 times 9, what can we say about its two subgroups and its three subgroups, that is p-subgroups for the various primes? This is the idea behind the Sylow theorems, developed by Norwegian mathematician Peter Sylow. The Sylow theorems address the following questions of a finite group G. How big are its p-subgroups? How are the p-subgroups related? How many p-subgroups are there? And what can we say about their conjugacy classes? Like which ones are normal? The Sylow theorems can be used to classify all groups of order 12, and we will do this in the next lecture. We've already seen them all, and here's a picture of their subgroup lattices. What patterns do you notice about the two groups and the three groups, that is the p-subgroups for the two primes dividing 12? I mentioned this in the introductory summary a few slides ago, but it helps to see a picture. Notice how all the p-subgroups come in towers. The blue towers are the two groups, and the red towers are the three groups. Notice how the tops of the towers form a single conjugacy class. And notice how the sizes are somewhat restricted. Even though 5 isn't very many, this conjugacy class, the top of the 2 tower, either has size 1 or size 3. And the top of the 3 tower either has size 1 or has size 4. That is due to the third Sylow theorem, which we'll see in the next lecture. In this lecture, we will establish that the p-subgroups come in towers, and there's only one tower for each, and the top is a single conjugacy class. We're going to use the same notational convention that we did in the previous lecture, but I want to add a definition. So G will be a finite group of order p to the n times m, where p is a prime that does not divide m. In other words, p to the n is the highest power of p dividing the order of the group. A subgroup of order p to the n is called a Sylow p-subgroup. Previously, I called it a maximal p-subgroup, but this is what they're usually called. I'm going to use this notation to denote the set of Sylow p-subgroups, and NP is the number of Sylow p-subgroups. I want to mention that some books and sources will write p Sylow subgroups. And even though I usually use this, it's sometimes helpful to use p Sylow as an adjective. So we say that this group is p Sylow. And I don't actually remember if I do that offhand or not, but just to let you know, if you do hear me say it, that's what it means, and you also might see it elsewhere. There are 3 Sylow theorems, and loosely speaking, they describe the following about a group's p-subgroups. The first one describes their existence. In every group, p-subgroups of all possible sizes exist, and they are nested. The second theorem says that all maximal, or Sylow, p-subgroups are conjugate. And finally, the third one says that there are strong restrictions on the number of Sylow p-subgroups. Together, these place strong restrictions on the structure of a group G with a fixed order. Throughout this lecture and the next, we will have a running example of a mystery group G of order 12. And we will, as we go through the Sylow theorems, see how much we can deduce about the structure of G. And then by the end, in the next lecture, we will classify all groups of order 12. We already know a little bit about G. By Cauchy's theorem, in the previous lecture, remember that was if a prime P divides the order of a group, there is an element of order P. This means that G must have an element A of order 2 and an element B of order 3. In other words, if you draw its 6 elements, you know that there's a subgroup of order 2 and a subgroup of order 3, generated by, let's say, A and B. In terms of the subgroup lattice, it looks like this. There's a subgroup of order 3 and a subgroup of order 2, and we don't know what else. Once again, using only the fact that this group has order 12 and the Sylow theorems, we will uncover as much about its structure as we can. The first Sylow theorem says that G has a subgroup of order p to the k for each power of p dividing the order of the group. Also, every non-Sylow p-subgroup, that is, every p-subgroup that is not maximal, sits inside a strictly larger p-subgroup. Let's prove this. We will induct on k, which is the exponent of p. So the base case, the trivial subgroup has order p to the 0 and is contained in, well, a cyclic subgroup of order p, because we know there is an element of order p. So there's some x of order p by Cauchy's theorem, and that contains a trivial group. So here's a group of order p to the 0, and here's a strictly larger group, p-subgroup, that contains it. Now we'll take an arbitrary p-subgroup that's not maximal, not Sylow, and we'll show that there is a larger p-subgroup that contains it. So now, suppose that H is a subgroup of G of order p to the k, which is strictly less than p to the n. Let's draw a picture of the subgroup lattice. This is how the proof is going to go. So we're going to have G, and we have H down here, and here's the trivial group. And let's write the order of these elements, or these subgroups, I mean. So G has order p to the n times m. H has order p to the k. We know from the previous lecture, the so-called normalizer lemma, that the normalizer grows. Remember, in p subgroups, the normalizer of a non-maximal subgroup, the normalizer will grow, and the index and H and the index of H in the normalizer is going to be a multiple of p. So that means that the normalizer is going to be, say, somewhere up here. And this has order p to the k plus some j, where j is bigger than 0, times, let's say, r. And we know that H is normal in the normalizer. And what that means is that we can quotient out by it. So we can't guarantee that H is normal in G, but again, it's always normal in its normalizer. So let's consider this quotient group. And by the correspondence theorem, the subgroup lattice looks like this. So the normalizer mod H, this is H mod H. And now let me write the order over here. So this has order. So what's the order of this? It's a multiple of p because it's a larger power of, remember this grows and it's a multiple of p. So this is going to be p to the j times r. So this group, the order is so p divides the order of this quotient group, which means that there is an element in this quotient group of order p by Cauchy's theorem. So an element, that means that it's an element of order p means it's a cyclic subgroup. So it's generated by some coset AH. So this has order 1 and this has order p. And then by the correspondence theorem, this coset here corresponds to some subgroup over here. So I'm just going to call that, how about H prime? So think of this as a subgroup of shoeboxes with the lids off, using the analogy that we did in chapter 4 in the correspondence theorem. So here's a picture of this. This is the normalizer of H. This is H. This is AH. This is A squared H. And so forth. And this is A to the P minus 1 H. So how many elements are in this subgroup? Well, there's P to the K plus P to the K plus P to the K plus each of these cosets has order P to the K, and there's K of them. So you add those up and you get P to the K plus 1. So this subgroup here has order P to the K plus 1. It's literally the union of all of these cosets. So it's all the elements in here. And this, of course, is contained in the much larger group G, which is up here. So how much of this do I want to write down? I would just say, let's just say by Cauchy's theorem, there exists an element AH in the quotient of the normalizer, a quotient of by H of order P. Oh, and it's probably worth saying that that P divides the order of this by the normalizer lemma of last time. So, and then we can, I don't know if I need to write this down, then we could say, by the correspondence theorem, the union of the cosets of this subgroup, so that is the union of A to the I times H, is a subgroup of G of subgroup of the normalizer, and therefore of G of order P to the K plus 1. So I encourage you to write this up formally. It's good practice to do, but I like this proof because it really involves the normalizer lemma that we used, Cauchy's theorem that we recently proved, and the correspondence theorem. And there's a really nice picture in terms of these subgroup lattices. Let's return to our unknown group of order 12. By the first Sylow theorem, this element A is contained in a subgroup of order 4, which could be V4 or C4, or maybe G's got both. So we have this motif or that motif in the lattice, and then we know we have a C3 subgroup as well. The second Sylow theorem says that any two Sylow, that is maximal p-subgroups, are conjugate. And if they're conjugate, they're thus isomorphic. So in other words, in the previous slide, we just eliminated the possibility of there being a C4 and a V4 subgroup. We will actually prove a stronger version of this, which easily implies the second Sylow theorem. Sometimes this is called the strong second Sylow theorem. It says if we have any Sylow p-subgroup and any other p-subgroup, so not necessarily p-Sylow, so this is a maximal one and this is something else, then K is conjugate to some subgroup of H. Let's see a picture of this. So the second Sylow theorem says if we have two Sylow p-subgroups, that is two subgroups of order p to the n, H and H prime, we can always conjugate H prime to get to H. The strong version says if we have any p-subgroup, might not be maximal, might have order p to the I, then we can conjugate that to get to something directly underneath, contained in the first one. Now notice that if we're just looking at subgroups of order p to the n, then that implies that we can conjugate this to get to exactly H. So this is indeed more general. The proof of this and the third Sylow theorem will involve a clever group action. Let's let S be the set of right cosets of H. That is our Sylow p subgroup. And now let's let the group K act on this set by right multiplication. So that is when we press the little K button, that's the permutation that sends each right coset HG to HGK. So until the Sylow theorems and the previous lecture, we would normally have G act on a set of cosets. But now we're letting this subgroup, which might be smaller, act on the set of cosets. So it's like we aren't allowed to press as many buttons on the switchboard. The first thing I want to do is remind you of the p-group lemma. Because our normalizer lemmas were basically applications of that, and this one will be as well. And so for this one, remember what this says is if we have a p-group, in this case K, acting on a set S, then the number of fixed points of the action is equivalent mod p to the size of the set. So our set here has order m because H is a Sylow p subgroup. So the order of H is p to the n. The order of G is p to the n times m. So the order of, let's just write, the number of cosets of H and G is the size of G divided by the size of H, which is m. And that is not a multiple of p. So in other words, the right-hand side is not 0 mod p. Because this is not a multiple of p, because p to the n is the largest power of p that divides the size of the group. Okay, so now what? We're trying to show that K is conjugate to some subgroup of H. So we want somehow to find some element G such that GK, G inverse, is contained in H. So some conjugate of K is in H. And here's what I claim. any fixed point of this action, if we take the representative, that G is going to work. And we know by the p-group lemma that there cannot be 0 fixed points because the number of fixed points mod p is not 0. So that's a game. Let's first of all show that a fixed point does what we want, and then we know right away that there has to be at least one fixed point. So let's check what a fixed point is. So this is a coset HG such that, well, by definition, if we take this coset and we press the K button, a little K button, we get back the same thing. So in other words, HGK equals HG for all elements in K. Now what can we do with this? Well, there's not much. We can move the G over and write HGK G inverse equals H for all K in K. And now by our so-called boring but useful coset lemma, I've said that like probably 20 times already in this video series, that's equivalent to saying that GK, G inverse, is in H for all K in K. Right? H times some element is equal to H. That means that element is in H. Now, what does this mean? This means if we take an arbitrary element in our subgroup K and we conjugate it by G, we get inside of H. And that's equivalent of saying G big K, G inverse. So again, this is a little k, this one is a big K, is contained in H. And that's what we wanted to show. H is conjugate to some subgroup of H. So an element, so K being conjugate to some subgroup in H by an element G is equivalent to that coset being a fixed point. And then by the p-group lemma, we know that the number of fixed points has to be equal to the size of the group mod p, and that since that's not a multiple of p, that's a non-zero number. So now the result follows by the fixed point lemma. So, or sorry, by the p-group lemma. So by the p-group lemma, the number of fixed points mod p is the size of S, which is not 0. So such a coset exists. And we're done. Isn't that a neat little action? You know, I guess one downside of it is most of us, if we're trying to follow our nose, probably are not going to come up with this action. Or even if we do, we may not think about, let's look at fixed points. It's one of those ones that once you see it, you're like, okay, yeah, that makes sense, but I probably would not have gotten there organically the first time. And that's okay. Not all of algebra is follow your nose and just do the proof. Let's now revisit our unknown group of order 12. By the second Sylow theorem, all Sylow p-subgroups are conjugate and hence isomorphic. That means that we can eliminate the following hypothetical subgroup lattice of a group of order 12. So there cannot be a C4 and a V4 in there both because those are maximal two subgroups. So that is not possible. Let's now revisit a familiar example. We saw this in chapter 3 in the lecture on products. I think that was 3.7 and maybe somewhere else as well. So this is the alternating group A5, which is the smallest non-abelian simple group. And I don't remember if I've proven it or just kind of hand waved of why there cannot be a normal subgroup in here. I mean, it looks reasonable that, these A4s are all conjugate, but, maybe these are all normal. We've seen things like that with the quaternions, the maximal subgroups all happen to be normal, even though they look like a conjugate fan. Well, let's highlight the p group towers. So this is p equals 2, this is p equals 3, and p equals 5. By the second Sylow theorem, the tops, as the Sylow p subgroups, are all conjugate. So now we know that the V4s are conjugate. So that means that the normalizer of each of these has index 5, because that's the size of the conjugacy class. So I'm going to pick a new color. Let's do purple, and I'm going to draw, for each one of these, I'm going to draw an arrow up to its normalizer. So I'll just do it for this one, and the others are similar. So what about C5? So the C5s are contained in a size 6 conjugacy class. So the normalizer has to have index 6, and that's these D5s right up here. So that points at the normalizer. These C3s are in a size 10 conjugacy class, so their normalizers all have index 10, and they're each contained in a unique subgroup of index 10. So there are those normalizers. Now, by the single parent property, these are all conjugate. These have to be conjugate as well. And so these are not normal. So the normalizer of each one, well, it can't be A5 because it's not normal, so it has to be itself. So similarly, the normalizer of these are all conjugate by the single parent property. All of these must be as well, so that each one of these is its own normalizer. And same thing over here. Okay, so what about these subgroups? Are these all conjugate? I mean, we know that the V4s are conjugate, but that doesn't necessarily mean that we can permute the order of these anyway, which way you want. So this C2 is conjugate to one of these C2s, but isn't necessarily conjugate to all of the blue C2s. Well, to answer that, in chapter 6, we'll see that in S5, well, we already know that the C2s are that these elements are products of pairs of transpositions. Those are conjugate in S5, and what we'll see is that when we pass to A5, we reduce the number of things we can conjugate by, so the conjugacy class has to either stay the same or split in 2. And there's 15 elements here, so it can't split in 2. But we don't yet know that. And by the way, we will prove that by looking at the index of the centralizer, which will either stay the same or half of it will be in the alternating group. But right now, we do know that A4, we understand this subgroup. We know that A4 contains 4 C3s that are all conjugate and 3 C2s that are all conjugate. Remember, we've seen that subgroup lattice quite a bit. So these red C2s are all conjugate in this A4, so they're all conjugate in A5. And in particular, all of the C2s of each color are conjugate. And because these are conjugate, I can bring a red one to a blue one or to a green one, etc. So again, we know that all of these things are conjugate. These triples are all conjugate. And then we know that we can take any one of these triples to any other of these triples. So what that means is we can erase this and we can say that all of these things have to be conjugate in the first place. So it's always good to analyze these subgroup lattices, use what we know across various chapters, things like index of normalizers and conjugate elements in the alternating and symmetric group and things like that, to analyze and say what we can about a subgroup lattice. So those are conjugate and those are conjugate. And finally, we have one more slide, and what we're going to do there is show the following. So here's what we know. We know that for a p subgroup, if we take its normalizer, it always gets bigger. So in this case, the normalizer of this has one of these has index 15. Actually, I should probably write that. So we go up here, and then we take the normalizer of this, we go up here, and then we take the normalizer of this, and we stay there. So what we'll show is that anytime that we have a Sylow p subgroup, so these, remember, are the only p subgroups that are allowed to be totally unnormal. That is, they could be their own normalizers. Anything else underneath cannot be its own normalizer. But in this case, they're not. We take the normalizer and they grow. But what we'll show is that you can only grow once. In other words, if you take the normalizer, then, well, there's two, and it grows. Then you take the normalizer again, it has to stay the same. Now, if this were normal, we go up here, and we take the normalizer, of course, it stays the same. So whether or not this subgroup is normal, we can and we will say that the normalizer of a Sylow p-subgroup is just equal to the normalizer. In other words, taking the normalizer twice, the second time we take the normalizer, we stay where we are, regardless as to whether or not we are at the top, in which case it's trivial that happens, or somewhere below. Using our language from chapter 3, in the previous example, all Sylow p-subgroups are moderately unnormal. And the normalizer of each Sylow p-subgroup was fully unnormal. In other words, it was its own normalizer. So we will prove that the normalizer of the normalizer, not of any group, but of any Sylow p-subgroup, is equal to the normalizer. Formally, let P be a non-normal Sylow p-subgroup of G. Then its normalizer is fully unnormal. So once again, if we start at G and we have a normal Sylow p-subgroup, the normalizer and the normalizer, we do it twice, the same as doing it once. But what this, so that's the trivial part of this. But what this is saying is that if we take the normalizer and we don't get to the top, then we do it again, we'll stay there. In other words, this subgroup is its own normalizer. It's fully unnormal. This, I mentioned this back in chapter 3. This is one reason why I like these terms, moderately unnormal and fully unnormal, because they're useful, especially in Sylow theory. I can say things like this. I can say p-subgroups cannot be fully unnormal unless they are Sylow. The normalizer of a Sylow p-subgroup is either the whole group or it's fully unnormal. Okay, so let's prove this. And we'll show that the equivalent statement that the normalizer of P is equal to the normalizer of P. And let's draw a picture of this. So here is the trivial group. Here is P. Here is the normalizer of P. And here is G. So G has order P to the n times m. P is order P to the n. This is order 1. And the normalizer has order P to the n times r. And we're going to assume that the normalizer, this is moderately unnormal because this statement here is trivial if P is its own normalizer, because you take the normalizer of the normalizer, you get the same thing. And it's also trivial if P is normal, because the normalizer is G, and then the normalizer of that is the same thing. So this is only interesting if this is moderately unnormal, so of order P to the n times r. Now, P is Sylow in p-Sylow in G, so that means that, and also it's a non-normal subgroup, which means in G that there is some conjugacy class of, let me say like P1, P2, I don't know, Pi, etc. There's a bunch of subgroups like this, and these things, there's going to be intermediate subgroups as well, so there'll be things right down there, etc. But this is like the P group tower that I've been coloring. So P, let me highlight this, make it darker. This is Sylow in G, but it's also Sylow in the normalizer. And we know that it is normal in the normalizer. Every subgroup is normal in its normalizer. Now let me remind you of something. Note that a Sylow p subgroup, so I'm going to write it as P. P is normal in G if and only if NP equals 1, i.e. it's the unique p-Sylow subgroup. Now, why is that? Well, we know that any time that there's only one group of a certain order, it has to be normal, because every conjugate has to be itself. So this direction is always, but the other direction is by the Sylow the second Sylow theorem. So if P is normal, so we know that there might be multiple conjugacy classes of order 2 subgroups in like D4 or D6. But by the second Sylow theorem, all Sylow maximal subgroups are conjugate. So if P is normal, and we know that it has to be conjugate to every other subgroup of its order, then it has to be the only one. So this is by the second Sylow theorem. So given that P is normal in its normalizer, that means that this is the only one of these Sylow p-subgroups that is contained in the normalizer. In other words, all of the other subgroups, Sylow p-subgroups, have to be contained in other, in other words, none of these subgroups can be contained in the normalizer. So let's write that down. So P is normal in its normalizer, as every subgroup is. So by the second Sylow theorem, it's the unique p-Sylow subgroup of the normalizer. Okay, so now what are we going to do? Well, let's take an element. So we want to look at now the normalizer of the normalizer. So let's take an element of something that normalizes this. So let's take an element x that is in the normalizer of the normalizer. So in other words, we're going to take the normalizer of the normalizer. We're going to take an element x that's in here, and we will show that x actually has to be in there. In other words, these things have to be the same. So how are we going to do that? So, well, so by definition, x normalizes the normalizer. So let's just write this down. X times the normalizer of P times x inverse has to be the normalizer. So now what? Well, here's the thing. If x normalizes this, then it's going to conjugate P to some other subgroup in here, but there's only one subgroup of order P to the n in here. So that means that xp x inverse has to be equal to P itself. So let's write that down. So xp x inverse has to, since P is in, maybe I should write, this is almost trivial, but since P is in the normalizer of P, then we can say that xp x inverse has to be in x ng of P x inverse, which is the normalizer of P. And now what? Well, this thing right here, that is p-Sylow, of course, in G, but it's also p-Sylow in the normalizer. But the normalizer has a unique Sylow p-subgroup, a unique subgroup of order P to the n, which is P. So that means that xp x inverse equals P by uniqueness. So that we just took something x in the normalizer of the normalizer, and we showed that it normalized P, and therefore it's in here. So this is indeed equal. And that's the end of the proof. Isn't that neat? So that's the end of the first two Sylow theorems. We established these P group towers, and that the tops are conjugate. And what we'll do next time is we'll learn how big these tops can be. There are some pretty strong restrictions. We'll see that the size of this conjugacy class has to divide M, which is the index. That's this M right here. but it also has to be equal to 1 mod p. And together, this places strong restrictions on the size of these conjugacy classes, so strong that in many times we can actually conclude that the number of Sylow p-subgroups, in other words, this number np, is equal to 1. And whenever we can conclude that, we know there's a normal Sylow p-subgroup and that the group cannot be simple. So we will use this to prove in many cases for a lot of different orders, things like any group of certain order cannot be simple because there has to be a normal Sylow p-subgroup. Or sometimes we can say there's either a normal Sylow 2 subgroup or a normal Sylow 3 subgroup. And there's even trickier things we can say as well. Sometimes we do a clever group action and we can show that the kernel cannot be trivial and cannot be the entire group. So it's kind of like integration, where there's a whole bunch of like little tricks and exercises you can do that you might not have thought of originally. But it is a pretty powerful technique. And we're almost done with the Sylow theorems, and we're almost done with chapter 5. So don't go anywhere. I will see you next time.